All right, I'm going to do a review here for Chapter 6. We'll just go through the examples here in the back of the chapter. You should have already read through the chapter. You should have already looked at the homeworks for this chapter. This is just to prepare you for the Chapter 6 and 7 test coming up. Okay, so this is on page 325 here in your book. This is the review problems for Chapter 6. We're just going to start here with number 2. So determine whether the distribution is a discrete probability distribution. If not, state why. Okay, so a discrete probability distribution, discrete meaning that the values of the data itself is either whole numbers or at least countable. And then a probability distribution is that if we do look at the probabilities of each of the outcomes, there's two things that you have to worry about. The first thing is that the probabilities always have to be in between 0 and 1. The second thing is that the probabilities always have to add up to be exactly 1. And that's what we're checking here. So for A, all of these probabilities are in between 0 and 1. That's fine. But if we add all of these together, so just real quick, the 0.34 plus the 0.21 plus the 0.13 plus the 0.04 plus the 0.01. So because those only add up to be 0.73, A would not be a probability distribution. I'm not going to bother doing B. I'm almost certain that if you do add these up, it's going to work out. So if they do add up to be exactly 1, then yes, it is a probability distribution. Okay, moving on. Number 3 here. Stanley Cup. Stanley Cup is a best-of-7 series to determine the champion of the National Hockey League. The following data represents the number of games played X in the Stanley Cup before a champion was determined from 1939 to 2015. Note there was no champion in 2005. The season was canceled. Okay, so again, the X here, this represents the number of games played out of 7. Frequency is the number of times that number of games happened. Part A. Construct a probability model for the random variable X, the number of games played at the Stanley Cup. So what I'm going to do is I'm going to come over to this OneNote here, and we'll just kind of copy over what we already have. So we have our outcomes 4, 5, 6, and 7, the frequency of those outcomes. Okay, great. A probability model is a table that has the outcomes, which we already have, and then the probability of those outcomes. So what I'm going to do is I'm going to add another column to this table for probabilities. The way we're going to find those probabilities, if you remember back from chapter 5, is we're going to be doing the empirical rule for probability. Basically looking at the number of total outcomes that we have here in our frequency, and then just dividing each of the individual frequencies by that total. So in our calculator, what we'll do is we'll just add up all of the frequencies to get the total. So 20 plus 18 plus 22 plus the 16. So we had a total of 76 Stanley Cups played. And we're just going to look at each of these individuals and then divide it by that 76. So that first outcome of 4, there were 20 times that happened out of the total 76, and we get 0.26. So I'll put that here for the probability of 4 games played, 0.26. I'll do the same thing for 5, so that's going to be 18 total times that happened out of the 76. So that's 0.24, rounding that to 2 decimal places. 6 games happened 22 out of the 76 times. 0.29. And then 7 games for the Stanley Cup happened only 16 times. So that's 0.21. All right, and you can check it to make sure you did it right. These should add up to be 1. Now, they might not add up to be exactly 1. They might only come out to be like 0.99 or 1.01. And that's because we rounded it to 2 decimal points. But if we didn't round it, it would add up to be exactly 1. But that's it for part A. That is what we're going to call the probability model, the outcomes and the probabilities. Moving on, B, graph the discrete probability distribution. Okay. So this is not something that I can necessarily have you do because this is an online class and they just don't have the tools to do it. You'd have to pick multiple choice answers of which one is right. But this is what the graph would look like. So we have our axes here with the outcomes, the discrete outcomes going along the horizontal axis, and then the probabilities of those outcomes going along, the vertical axis here. So let's see, we have mostly stuff in 20% range. So what I'll do is we'll do 10% there, 20% here, 30% up here. Okay, so for when you're graphing probabilities like that, we're going to be using kind of this weird graph, and you'll see what it looks like. So outcome of 4 goes up to 26%, which is a little bit more than halfway between the 2 and the 3. So what you do is you just draw a vertical line, and then when you hit the 26, you put a little dot at the top. 5 is at 0.24, so that one's going to be just a little bit below the other one. 6 is at 0.29, that's almost to the 3. 7's at 0.21, so just a little bit above the 2. So it would look something like that. This is kind of uniform, I would say, so a uniform distribution here. Okay, so that's that. C and D are the most important parts of this. Compute and interpret the mean of the random variable, and then D, compute the standard deviation of the random variable. I hope you have not been doing this by hand, because this is something that your calculator can do for you very easily. So what you want to do is you want to go into the stat of the calculator, just like we did back in chapter 3. Edit the table, clear out anything that may be in there. And then you're just going to put the outcomes there in the first column. And then the probabilities in the second column. So that's these numbers that we got here, the 0.26, 0.24, 0.29, and the 0.21. It does work if you put the frequencies in this column. It works just fine. But because we're technically supposed to be finding the probability mean of the random variable, we're going to put probabilities here. Okay, so once you have it all typed in like this, we're going to go back into stat. We're going to go over to calculate. And again, just like back in chapter 3, this one VAR stats button, this is fine. So L1 is in the list. But we do have items typed into the second column. They're technically not frequencies, right? They're probabilities, but the calculator doesn't know any better. So make sure there's an L2 in the frequency list. Great. And so we get these numbers. So we get this mean here, 5.45. So that is going to be the mean of the random variable. Notation-wise, the mean of the random variable, we write like this, mu sub x. So that was that 5.45. I'm going to round that to 5.5, again, because we have whole numbers. And whenever you have whole numbers, you round to 1 decimal point. It's always 1 more decimal point than the data values that you're given. You were asked to interpret this, so let's just kind of write a little sentence about what this means. Now, there is another name for this mean. It's called the expected value. 5.5 would be the expected value here for our outcomes. And the little sentence that we could write is something like, for the Stanley Cup in a best of 7, we would expect around 5.5 total games played. So just something like that. So basically just kind of explaining what the experiment is doing and then saying that we would expect whatever the expected value comes out to be. Okay, also in the same menu, notice that when we're talking about, would you stop it? Dog scratching himself. Notice that the sample standard deviation is actually empty. It's empty because the calculator knows that this is a probability distribution, and there is no such thing as a sample standard deviation for probability distribution. You only get this population one. So the standard deviation for the probability distribution here, I'm going to round that to be 1.1. So sigma sub x 1.1. Good. So that's it for number 3 here. Moving on. Number 4, it looks awful. We'll do it though. So number 4, expected value of 3-card poker. A popular casino table game is 3-card poker. One aspect of the game is the pair plus bet, in which a player is paid $1 of amount for any hand of a pair or better, regardless of the hand the dealer has. The table shows the profit and probability of various hands of a player playing the $5 pair plus bet. Okay, and we get a bunch of stuff here. So we get the outcomes of the different hands that you could win. It doesn't matter what all these mean. You get the amount of money that you win, and then you have the probability of that particular hand occurring. Okay, I'm going to do this all in the calculator. So the question is asking us to find the expected value. The expected value is the same thing that we found here in part C, the mean of the random variable. So we're going to go into stat, we're going to edit the table, clear out what we just did from question 3. Okay, so when you're finding the expected value, you need the outcomes in the first column. The outcomes of betting is the amount of money that you're going to get back. So this is what I'm going to plug into the first column here. So depending on the hand that you get when you play, these are the outcomes. Okay. Beside these outcomes, we're going to plug the probabilities here. Now they're all in fractions, which is just fine. You can type them into the calculator just like that. So that first outcome has a probability of 12 out of 5,525, and it gives you a little decimal for that. The next one, 1 over 425, gives you the decimal for that, and so on and so forth. Okay, so we're finding the expected value from this, which is the same thing that we were doing before, right? And finding the mean of the random variable. So once you have the outcomes in the first column and then their probabilities in the second column, go back into stat, over to calculate that one VAR stats. Make sure if you have a menu, it makes sense that you do have L2 in the frequency list, and then calculate. The number we're looking for here is this mean. We get a mean of negative 0.12. Remember that we're dealing in money here, so really that's like 12 cents. Every single time you play 3-card poker and you bet $5, you have an expected value of losing 12 cents. Now, of course, that's not going to happen every single time. This is what would happen after a long period of time of betting $5 over and over and over again. If you were to sit at this table and bet $5 on 3-card poker for the rest of your life, then on average, you would be losing 12 cents every time you played the hand. Okay, so that's the answer to part A here. What's the expected value? Part B, if you play the game for 4 hours with an average of 35 hands per hour, how much would you expect to lose? Okay, so we're playing for 4 hours. Every hour we played 35 hands, and every time we play a hand, we lose 12 cents. So I'm just going to multiply all these things together. 4 hours, 35 hours per hand, times the fact that we lose 12 cents per hand, and we get negative 16.8. So probably not as bad as you would think, right? You're playing for 4 hours. You're only going to lose about $16. Okay. Awesome. Great. Okay. Moving on. I'm skipping 5. 5's kind of lame. I'm skipping 6. 6 is kind of lame too. 7. So this will be the last one that we do here in this video. The video is getting a little bit long. According to a Gallup poll, 60% of U.S. women 18 years old or older stated that the minimum driving age should be 18. In a random sample of 15 U.S. women 18 years old or older, find the probability that, and then a bunch of different things here. Okay, A. Exactly 10 believe the minimum driving age should be 18. This question is known as a binomial distribution. It's binomial because of 4 things that has to happen. So I hope that you read through the book and you looked at those 4 things and you understand what a binomial distribution is. Just know that this is a binomial case. With binomial distributions, do not ever use those formulas. They're awful. Use the calculator. We have 2 functions in the calculator that really help us out for this. So I'll show you where the functions are if you haven't seen them yet. So what you want to do is you want to hit second and then this VARS button to get to the distribution menu. This is going to be very important moving on for chapter 7, 8, and 9, but also here in chapter 6. We're going to look for binomial distributions, which you're probably going to have to scroll down a little bit. It's not on the initial screen here. So if we scroll down quite a ways, we see binomial PDF and binomial CDF. The binomial PDF is whenever you're looking for an exact number of successes. The binomial CDF is when you're looking for less than or equal to a number of successes. So let me go back to the book here. Just to read through the question again, 60% of women age 18 years old or older stated that the minimum driving age should be 18. In a random sample of 15 U.S. women 18 years old or older, find the probability that, A, exactly 10 believe that the minimum driving age should be 18. So what we have going on here is we're choosing 15 people, and what we want is we want those 15 people to have 10 think the minimum driving age should be 18. So because we need an exact amount, going back to the calculator, exact amount is the PDF. So we're going to choose that one. Hopefully you have a menu here. If you do not have a menu, I'll show you what to do next. So it's asking for a few things. First, it's asking for the trials. The trials is always going to be the total number of people that you're trying to find the opinion of. So there's 15 women that we're asking. The p-value represents the probability of success. The probability of success is the probability of one individual agreeing with the statement. That's this 60% here. 60% of U.S. women think that the driving age should be 18, so that's what we're going to plug in for the p, 0.6 for 60%. The x value is the number of successes, and remember we wanted exactly 10 successes out of the total 15. All right, and then we just paste. If you do not have a menu, then you need to type your stuff in just like this. The binom PDF 15, 0.6, 10, hit enter, and we get an answer here. So that's it. That is going to be the answer here for part A. So this was, what was it, number 7, I think it was? 7A came out to be 0.1859. That's the probability of selecting 15 women and having exactly 10 of them agree with the statement. All right, back to the question. B, fewer than 5 believe the minimum driving age should be 18. Okay, so here's where we're going to have to start being very careful. So I'm going back to the binomial distribution stuff. We're not going to select the PDF this time because we're not looking for an exact amount. We're looking for less than. Binom CDF does less than or equal to. So we have 15 trials. We have probability of success 0.6, but we have to be careful about the x value. We want there to be less than 5, but less than 5 is the same thing as less than or equal to 4. So I'm actually going to plug a 4 into here because I want less than or equal to 4 of the women to agree with the statement, which is the same thing as less than 5. All right, and we'll just paste, hit enter, and we got our number, 0.009 here for B. Oh, I guess 4 decimal places, 0.0093. Okay, back to the book. C, at least 5 believe that the minimum driving age should be 18. Okay, I'm not even going to use the calculator for this one. So at least is the same thing as greater than or equal to, but we can't do greater than or equal to. We can only do equal to the PDF and less than or equal to the CDF. So we're going to have to use other probability techniques for solving this one. If we want to do greater than or equal to 5, which is what the question's asking, right? We want the x value to be at least 5, which is greater than or equal to 5. This is the same thing as using the complement rule of 1 minus the probability of being less than 4. Right? So this is the complement rule from chapter 5. That's just the opposite statement. Probability x greater than or equal to 5, same thing as 1 minus the probability of x less than 4. But we've already found the probability, oh sorry, that's supposed to be less than or equal to. We've already found the probability of x less than or equal to 4 in the last question. So we're just going to do 1 minus that 0.0093, which is 0.9907. So that is going to be the answer to C. It's just the opposite from B. Okay, so I'm not going to bother doing the rest of these. The rest of these is just the same kind of stuff. You're using the PDF, the CDF, and then some probability techniques for getting these. But I hope you've already looked through the questions and they'll help me solve this on the homeworks to kind of help you out.